Hello guys, welcome to the Genius classes. So guys, in this video we are going to talk about the Heisenberg uncertainty principle. Also guys, if you're liking our videos and you're learning from it, then you can press the like button, press the subscribe button and share it with your friends. Also, if you want us to make videos on some particular topics, then you can comment down below, or if you want to contact us, then our number is in the description box. So guys, let's start with the Heisenberg uncertainty principle. So guys, in 1927, a scientist named Werner Heisenberg, stated his uncertainty principle. So what's the principle is? The principle says that it is impossible to measure simultaneously the position and the momentum of an electron. So this is the principle stated by the Heisenberg, which states that it is impossible to measure simultaneously the position and the momentum of the electron. It is not complex, it is very easy that you cannot calculate simultaneously the position and the momentum of an electron right on the same time. So it is the principle which is given by him. Now here is the mathematical expression which is given by the Werner Heisenberg. Let's study about it. Now, this is the mathematical expression given by the Werner Heisenberg. Delta x here is the uncertainty in the position. Delta p here is the uncertainty in the momentum. And h here is the Planck's constant. And its value is 6.626 into 10 raised to the power minus 34. So, this is the expression which is given by the Werner Heisenberg, and a relationship between the uncertainty in position and the uncertainty in the momentum. So here is something which we have to study about this relationship, the conclusions and the results from this relationship. Now, as you can see here, that the product of delta x, that is uncertainty in the position and the uncertainty in momentum, is constant. That is h by 4 pi. The value can't be changed. H pi value is constant, 6.626 into 10 raised to the power minus 34, and 4 pi values is also constant. So as you can see that the product of both of these are constant. Now can I write it as delta x is inversely proportional to delta p. As you can see, the product is constant, so we can write it as this, and we can find a relationship between the uncertainty in position and the uncertainty in the momentum. So they both are inversely proportional. So it says that if we try to measure accurately the value of delta x, means if we find the value of delta x very accurately, if we find the value of delta x accurately, means the value of delta x become very small, then the value of delta p will be very inaccurate or will be very uncertain, because they both are inversely proportional. Again, if we try to measure the value of delta x very accurately, means that delta x will be very small, then the delta p value will be less accurate. Same with that momentum. If we want to calculate momentum more accurately, then the delta p value will become very less and delta x value become large and less accurate. So this talks about the relationship between delta x and delta p. Now this is basically which was given by the Heisenberg uncertainty principle. Now we have to study this thing experimentally too. Now there is an experiment from which you can understand the things more better. This is the original path. This is basically the experimental setup which we use to study the Heisenberg uncertainty principle. The experimental setup says that if we want to measure the exact position of electron and the momentum at same time, then we use a radiation of light with shorter wavelength. Again, if we want to calculate the momentum and the position of an electron, then we use a radiation of light of shorter wavelength. Okay, this I will tell you why we use the shorter wavelength. Now, as you can see here, this is an incident ray of radiation of shorter wavelength on the electron. As this incident rays goes on the electron, it reflected back and it's seen on a microscope. This is a microscope. This is our incident ray, means we are ejecting photons on the electrons and the radiations are of shorter wavelength. Now as you are ejecting the photons on the electrons, these photons are reflected back by the electron, and now this is the new path. Firstly, electron is here when we are projecting we are ejecting the photons on the electron. Now after that, its new path will be this. It has to move in that particular path, that is its original path, but now after colliding with the photons, now it is the original path of the electrons. Okay, and the photons which are reflected back are seen on the microscope. Now let's study this more better. Now according to the principle of optics, which says that if you want to measure the position of a particle more accurately, then you have to use, and it depends upon the wavelength. Again, according to the principle of optics, which says that if you want to measure the position of a particle more accurately, then it depends on the wavelength used. Here we are using a short wavelength. Short wavelength we are using to measure the position of the electron. Now as we all know that the shorter wavelength have more energy. The shorter wavelengths of photons have more energy, hence it will change the momentum of the electron. Again, according to the principle of optics, which says that if you want to measure the position of a particle, here the particle is electron, then it depends upon the wavelength used. Now as we are here using the shorter wavelength for the measurement of the position of the electron, as we all know that now the shorter wavelength photons have more energy. They have more energy, so it will change the momentum of the electron. Now with the shorter wavelength, we can calculate the electron position, but we cannot calculate the momentum. Okay, now if we use a longer wavelength, then what happens? If we use a longer wavelength, the momentum will not be changed, but we cannot find out the position of the electron. As you can take an example, if you want to find out the thickness of the paper, then you use a meter stick which has units less than the units of the thickness of the paper. Again, if you want to find out the thickness of the paper, then you use a meter stick. Then you use a meter stick which has units smaller than the which has units smaller than the thickness of the paper. Okay, so here we use a shorter wavelength. If we use a longer wavelength, we will not be able to trace the location of the electron, and we can calculate its momentum. But now, what is the significance of this Heisenberg uncertainty principle in a today's life? Heisenberg's uncertainty principle has no significance in our real life, just like the de Broglie waves. They have no significance in our real life as such as de Broglie. There is no significance of Heisenberg uncertainty principle in our real life. We can prove it too. There is no significance, I have told you, that is in real life means there are macroscopic particles. Heisenberg uncertainty principle is applicable on microscopic particle but not on macroscopic. That's why I say in real life. In real life we deal with macroscopic which has greater mass, but microscopic particles are those which we cannot see with naked eyes and not even with a microscope. Now we have to prove this mathematically. Let's take a mass of, let's say, 1 milligram, and let's use the mathematical expression which was given by the Werner Heisenberg, which was delta x delta p greater than or equal to h upon 4 pi. Now let's put out the value. Here it's, let's use it, delta x dot delta v. We can write momentum as delta v dot m. Mass can't be changed, but velocity can be changed. So I have written delta v dot m. Now h upon 4 pi. Now I have removed here the equality sign into equal to into m. Delta v dot m I have multiplied it here. Okay. Now let's put down the values. H value is 6.626 into 10 raised to the power minus 34 upon 4. Value of pi is 3.14 into the mass. Now 1 milligram will be equal to 10 raised to the power minus 6 kgs. Now the calculation is very complex, so the result will be 10 raised to the power minus 28. Now as you can see, this value is very inaccurate and very insignificant, so we will not take this value and we ignore this. If you use a microscopic particle which has very greater mass, then the result will be very small and the value will be more insignificant. Okay, so it proves that the Heisenberg uncertainty principle don't work on the macroscopic particles, but it does work on the microscopic particle, which we also can prove. Now mass of an electron is 9.1 into 10 raised to the power minus 31. Okay, now apply this on I'm not sure actually here the mass of the electron, but it is around 9.1 into 10 to the minus 31. So the result will be 10 raised to the power minus 4. Since the value is significant and can't be ignored, so it shows that the Werner Heisenberg uncertainty principle is true for the microscopic particle and has no significance in real life. That means it has no proper significance for the macroscopic particles which have greater mass. So this is all about the Werner Heisenberg uncertainty principle. Thank you for watching the video. Must subscribe, must like, must comment.